Okay, hello again, everybody. Now we'll talk about choosing the right sequences with the right software. In this lecture, we'll talk about how to choose the right sequences. Of course, you have to carefully select the sequences what you are looking for. For example, a same protein family, and you would like to align to extract some more information, or if you, for example, try to take a protein family that share a common ancestor, this probably will be very or too large to entirely include it. So in this case, you have to pick the right sequences, which is a little bit of art. We will help you to give you a few guidelines for selecting the right sequences. First of all, what you are looking for? Are you looking for DNA or protein? In this case, if you most bioinformaticians prefer protein, because protein, try to pick it whenever it's possible, and you can turn them back into DNA later on. But if you are looking for non-coding sequences, for example, parts of the genome that is not translated to a protein, in this case, you can use DNA. Try to avoid, first of all, using a lot of sequences. So more than 50 sequences is not needed, except if you are looking for that. So don't try to have very different sequences. For example, less than 30% identity. So because the very different sequences always cause trouble. Identical sequences also never help. So don't also try to use identical sequences unless you have very good reason to do so. So in this case, avoid incorporating 90% or more, as we said before, unless you have a very good reason to do so. Also, try to avoid having partial sequences, because this causes trouble in computing and comparing sequences. So try always to keep in mind having complete sequence in your set, because mixture of complete and non-complete sequences or partial sequences or shorter fragment always cause trouble in your multiple sequence alignment. So in this case, try to have complete sequence as much as you can. Always try to avoid sequences that have repeated domains. Unless you don't have any other choice. But try to avoid them whenever possible, because they cause trouble, and especially if the number of domains are different. You cannot generate a proper alignment after having all what we said before, and you still cannot do this. So in this case, you can use local multiple alignment methods such as Gibbs sampler or Pratt, and these two methods will help you to for pattern extraction and motif extraction, and in this case it will help you to find more information that help you in the alignment. Okay, so for carrying out phylogenetic analysis, if you have a set of coding DNA sequences, this will be very easy to translate your DNA sequence into protein, and then of course perform the multiple sequence alignment on your protein, and then you can thread them back onto protein multiple alignment using Paltonal or Protogen, from Tcoffee. So first of all, if you have a DNA sequence that is can be translated into a protein, so use the protein for making the multiple sequence alignment, and then, as we said, thread them back to your DNA. So choosing the right number of sequences, try to pick between 10 and 15, and after getting something interesting, you can increase in size. You can put more and more sequences. And as we said, there's no reason to put more than 50 sequences unless you would like to have an extensive phylogenetic tree. In this case, you can put more and more, and this depending, of course, in your project and what you are looking for. Why we try always to avoid big alignment or much sequences or more than 50 sequences, because computing is of course is a difficult, building big alignment is difficult, displaying and making an or using them, or even making an accurate alignment with a big set of sequences is difficult. So we always try to avoid having a big set of sequences. So we always also we choose sequences that are not very similar and are not very different. So we try to compromise between similarity and new information. So in this case, we try to avoid, as we said, not very similar, not very different. We try to compromise with that to get a new information, and then we can extrapolate annotation. So this we always have to keep all these points in mind and try to find as distantly related as possible, and without requiring too many gaps in order to properly align. This is the general rule. The general rule is to have sequences distantly related as possible without requiring too many gaps. Two things we have to keep in mind also. Programs that try to make multiple sequence alignment don't like, as we said, sequences that are very different from each other, sequences that are need long insertion deletion to be aligned. So this we always have to keep these 2 points into our mind. Don't have them so because to have a properly aligned sequences. You can of course gather your sequence using blasts. You can just have a characterized sequence that have good annotation and experimental information, and then you can just do blast to get more similar sequence to what you are looking for. Or if you have uncharacterized sequence, you have to distinguish between the conserved position, and you have to in this case get some contrast. You have uncharacterized sequence to get some contrast. So this is the 2 reasons why you can make or how to gather your information using gather similar sequences using blast. Sequences that are not so similar, as we said, to the query are properly homologous. Sequences that are so similar, to the query are properly homologous. So that's why when we do blast and we see that there is a bit of similarity between our sequence and between other sequences when we get the blast result, so we simply try to get this sequences and put them and use them to build a multiple sequence alignment because they properly are homologous. In this case, this will be, we call them as hits or matches. So we try to grab these matches or hits and try to extract them and build a multiple sequence alignment with these hits or matches. Of course, there is a lot of good programs for that. As we said before, ClustalOmega is one of them, the most commonly used, and it's used hidden Markov profile to profile technique. And of course, Tcoffee is also the second famous. It's combine sequences, structure, and of course you can get evaluation for your sequence alignment from Tcoffee also, and it has many techniques in this package, and it's free, so it's good news. And of course, the third one and third famous one is the muscle. It's the fastest one, and you can get a lot of sequences when you want. If you would like to build a big alignment, you can use muscle, and you can have a large set of sequences in this program, and it will make it easily for you. Okay, thank you, and we'll look at lecture 3 and continue with that.